So the next speakers are Iryna Kyrychenko and Daria Pronina, comparison of Redux and React hooks methods in terms of performance, Kharkiv National University of Radio Electronics. You're welcome.
Yeah, hello. It is said that you're disabled participant screen sharing.
You can try once again.
Okay, I see. So it looks like I need to enable it in my settings, and I probably have to relaunch Zoom. Yeah, I'll rejoin in a moment.
Okay.
Okay, so can you see my screen?
Yes. Yeah, I can see it.
Okay. Good afternoon. A report is presented on the topic comparison of Redux and React hooks methods in terms of performance. Authors are Daria Pronina and Iryna Kyrychenko from Kharkiv National University of Radio Electronics. The process of creating web applications has evolved and become easier over the years. By operating with various high-level abstractions, developers can design and implement complex systems without having to make any fundamental decisions over and over again. Talking about state management, thousands of different libraries implement various approaches to managing the state of front-end applications, making it hard to decide on the correct method for a particular project. Additionally, there are no real standards that can be used when choosing technologies for the development, and considering the amount of data in complex front-end application, the usage of the wrong method can lead to severe performance issues, especially on weaker devices like smartphones, tablets, and older computers. This makes a study on state management methods from performance point of view essential. The goal of this study is to compare Redux and React hooks methods for state management in React single-page applications and provide further recommendations based on the obtained results. React library was chosen for the study. It is a declarative component-based library and one of the most flexible libraries for user interface creation. The flexibility of React in particular lies in the fact that for a long time it was positioned as a library that solves only the task of presentation, making it possible to build user interfaces in the form of component tree. It is also very popular among the developers and has around 15 million of weekly downloads. The studies highlighted the shift towards single-page applications instead of traditional approach of creating multi-page applications. And the main goal of single-page applications is to offer faster transitions and user interactions, and to make the web application feel more like a native application that is running locally on the user device. In order to study the impact of different approaches on the performance, a simple front-end application was created with the functional requirements that are listed on the slide. In this way, it is possible to compare state management methods without any assumptions and result data modifications, since the experiment is carried out on the same data. Presentation part of the application, once implemented with React, remains unchanged during the study, while the state management is being implemented with React hooks and Redux approaches separately. Redux is a third-party library for state management that is used in front-end applications. At some point, it has become very popular. It has its advantages, such as scalability, and it helps make maintaining the application state predictable. The main concept behind Redux is that the entire state of an application is stored on one central location. The official React bindings for Redux are implemented and provided with Redux library. With these methods, React components can be attached to the application store or to some part of it. The global state of the application is read-only, and in order to make changes there, it is necessary to dispatch a corresponding action. Actions are plain objects that have type and payload. However, they are modified with a special library like Redux Sync, so it is possible to make network requests. Changes in the global state occur through pure functions. This means that these functions shouldn't have any side effects, and their code reduces. All these combined into a store, and it is passed to the React application by a special component provider. For React hooks implementation, no other dependencies are required except the React library itself with the version starting from 16.8. React hooks method provides an opportunity to implement all the logic directly inside components, whether it is a basic operation with state interaction with browser APIs, network requests. It's a straightforward approach, and at scale, it brings a lot of duplicated code as well as constraints logic to specific components. This increases the complexity of code supporting and lowers the degrees of code reusability. But this can be avoided by creating and using custom hooks. It is a function that uses built-in React hooks in order to provide a more complex functionality. In such a way, the encapsulation of all logic related to API or other state manipulations can be achieved. Built-in React hooks that were used are listed on the slide. These hooks are designed for storing memoized values, callbacks, and simple component state data, as well as performing side effects. Memoization is an optimization technique used primarily to speed up computer programs by storing the results of expensive function calls and returning the cached result when the same input occurs again. Custom hook user API was implemented. API that was used in the research is RESTful, and therefore the API calls can be easily reused by only providing the entity name in configuration and the callback. The influence of the chosen state management approach can be observed both on the output code and on measurements in the directly running application. The performance of web application can be degraded very easily by using wrong libraries, not only for state management. Google has created a model called Web Vitals for providing development guidelines to developers in the process of designing and building web applications, which are extremely important for providing an adequate user experience on the web. It is a useful tool for evaluating web applications performance, but most of those metrics are not influenced directly by the state management approach, but with other parts of front-end related part of the web application. Therefore, it was decided not to use the Web Vitals directly, but they were taken into account. It was assumed that the most impact of the state manager choice can be observed on the build size and while user interacts with the page. The bigger the build size, the more it takes for user device to download all the application files and launch it. Time that took to page to load and become interactive is a very important metric as it affects the potential user significantly. Taken into account everything mentioned, the metrics displayed on the slides were defined for the comparison. Measurements regarding the code size of the project are shown in the table. So basically we can see that Redux version took much more memory than Hooks version. For the calculation of the percentage delta of amount of code needed for implementing best methods, the following formula was used, where V1 is the size of code that was developed for implementing methods of the first entity, and V2 is the size of code for the second entity, respectively. The results in the table. The following formula is used for calculation of the reused code percentage. V1 is the size of code that is used by both entities, and V2 is the total size of code for both entities in kilobytes. As we can see in Hook's version, the reused code value is higher. Assuming that the following entities will take the same amount of code to be implemented as a second entity, the growth rate can be calculated by the following formula, where V1 is the total size of code for both entities in kilobytes, and V2 is the size of code for the first entity. The results of calculations are presented in the table. For measuring performance of the running application, Chrome DevTools were used. It's an interactive dashboard that has a lot of different tools for web developers included, and it is built in the Chrome browser. Among the presented tabs, the one called Performance may provide a lot of important information and shed some light on how it actually works under the hood. While storing application data, the memory of user device is consumed, as there are many ways of optimization with different data structures and approaches. The required size for the same data and in Redux and React hooks methods are not equal. The amount of memory was measured for different size of data stored in an array 10 times, and after that the mean value was calculated. As we can see, for Redux version, it took much more memory on the size of 200 elements. Applications are designed to be interacted with by users. Therefore, the responsiveness is another important metric in terms of performance. One of the possible interactions in the application is to create a new post that causes an HTTP request to the server and state update as well, that causes the page rendering. Google Chrome DevTools allows us to measure the exact time for this interaction. The example measurement for creation of the new post is shown on the picture. The actual consumption time to update state is calculated by using the following formula, where T is total consumption time and Ti is the idle time. The results of measurements are presented in the table. The average value was taken by measuring the interaction 10 times and afterwards calculating its mean. In this study, two methods of state management in React single-page applications were considered from a performance point of view, Redux and React hooks. Series of tests and measurements were carried out to get a complete picture of how each of the approaches affects performance. Redux approach requires a lot of boilerplates in order to implement the correct data flow and follow the main guidelines and concepts. In addition to that, React Redux library, as well as the library for creating asynchronous sections in order to make HTTP requests possible. That resulted in worse performance compared to React hooks approach. The study showed that creating the data flow logic is more complex in Redux and takes more code. Also, it took more memory for Redux to store the same amount of data in comparison to React hooks approach. The basic state change in operation consumed more time in Redux approach as well. To sum all up, it can be concluded that React hooks approach is more optimized from the performance point of view than the Redux method. In case of high importance of application performance, it is not recommended to choose Redux as a state management library in React single-page applications. Further research is required to confirm the results and the conclusions or to refute them. Complex web applications with several entities and additional application-wide state features such as notifications and authorization should be considered for further research. Other methods of state management should be compared in order to provide a clearer picture of the current state of state management in terms of performance. Thank you for your attention. The report is over.
Thank you for your presentation. So, dear participants, do we have any questions to the speaker? So don't forget that we have chat, and if some questions appear, you're welcome also to put them there. Thank you. Thank you for your presentation once again. So the next speaker is Viktor Hryhorovych, and he conducted a research on the topic analysis of scientific texts by semantic inverse additive metrics for ontology concepts, Lviv Polytechnic National University.
Yes. You see my presentation?
Yes, yeah, we can see it.
I begin. Semantic analysis of textual information is a problem that does not lose its relevance. It has to be solved when solving such tasks as shown on this slide, namely automatic filtering, classification, and clustering of text documents, automation of abstracting a given text, automation of evaluation of answers to open tests, automatic construction of a semantic network for a given text, etc. This paper will use semantic analysis based on inverse-additive metric that take into account the semantic distance between ontology terms in the text document being analyzed. Semantic analysis will be considered for scientific documents as such texts have a clear structure. To do this, introduce the concept of semantic distance between the terms of scientific text and the semantic weight of scientific text. The semantic weight of individual fragment of scientific text will be used to solve the problem of automatic abstracting. Related works, both works of philology and scientific articles in the field of information technology and computational linguistics are devoted to the semantic analysis of texts. Many quantitative characteristic approaches are essentially passing because they use a frequency approaches based on the number of occurrences of keywords. Some techniques use the conversion of texts into real number vectors and use the mathematical apparatus of vector algebra to quantify the corresponding text documents. Such approach are also reduced to the number of occurrences of certain keywords of comparison with a template, the basic body of textual information. Methods. Inverse-additive metric for ontology concepts. It allows calculating the distance between ontology concepts in the case when there are several paths from one concept to another. Define the distance from A to B between the concepts A and B as follows, formula 1, where Ni is the number of transition from concept A to concept B on the i's path, I from 1 to k. K is the number of different paths, then k be taken on the oriented graphs of particular ontology from concept A to concept B. Then the more paths there are between concepts, the smaller the distance will be. That is, the semantically closer the corresponding terms will be. Scientific distance between terms of scientific texts. Scientific texts have a clear hierarchical structure as shown in figure 1. Root level, root node is the title. Next level is the list of authors, keywords, abstract, titles of sections, reference list, etc. Next level is the titles of subsections. Other levels are possible. And final level is words in the same sentences. The distance between two terms in a scientific text should be defined to take into account the following first, repeated occurrences of each of these terms in the scientific text. Second, the hierarchical structure of the document. Third, the presence of many paths from each occurrence of the terms A to each occurrence of the terms B. And last, the distance between the corresponding concepts of these terms in the ontology. Semantic distance between terms of scientific text defined as shown on formula 4, where R from A to B is the semantic distance between the terms A and B from the ontology in the scientific text. And A is the number of occurrences of terms R in the scientific text, and B is the number of occurrences of the terms B in scientific text. I and B, K is the semantic distance between ith instance of the terms A and cut instance of the terms B from the ontology in the scientific text. Semantic distance explained the next feature. It is necessary to consider in what places of the text there are the specified terms. Suppose that any terms in the paper title, any in for example, tables list or abstract, any titles of subsections, any in the same sentences. Consider the example shown in this feature. Suppose that in the ontology used to evaluate a scientific text, the distance between concept A and B is equal to A. According to Formula 1, we obtain that the distance will be calculated for this formula. Then the more occurrences of ontology terms in a scientific text, the smaller the semantic distance between them. Next, semantic weight and semantic size of scientific text. For the semantic analysis of scientific text, it is necessary to define the concept of semantic weight. The semantic weight of scientific text related to a certain ontology is the sum of the inverse distances between all terms of the ontology in the scientific text as defined by Formula 5. Thus, the more terms there are in scientific text or its fragment, and the smaller the semantic distance between them, the greater the semantic weight of this text or its fragment. Automatic abstracting of scientific text based on the semantic weight of sentences. Semantic analysis of scientific text based on semantic weight will solve the problem of automatic abstraction based on the selection of sentences or paragraphs with the highest semantic weight. To do this, first define the sentences with the largest semantic weight. This method explained by Formula 6. Notation is developed. Next, we determine the degree of compression U in arithmetic abstracting. The result of S will include those sentences whose semantic weight differs from the maximum by no more than mu on the Formula 7. Thus, automatic abstracting will be implemented as a selection of sentences of compression of scientific text in 1 to mu times relative to the initial number of sentences based on their semantic weight. Calculation of the distance between the concept of ontology. Consider the fragment of ontology of computer science terms. It shown by on the figure 3, that fragment. Schematically, it may shown as a figure 4. It explains relationship use of between ontology terms, and it is the list of adjacent particles of the and the corresponding oriented ontology graphs demonstrated by figure 5. To simplify the calculation, discard all paths with the length of more than 4 transitions. Such a path will not be essential for calculating the semantic size of text. write down the result in the dictionary with the case and number transition. For optimization, we save the result of calculating the distance between a pair of terms, because the distance between the terms of ontology does not change often, only when editing the ontology. And at the beginning of the algorithm, we will check whether the algorithm has already been executed for this pair of terms. If so, we will return the result without the execution. Next slide explained. Semantic weight is the sum of the inverse distance between the ontology of terms in scientific text, as explained above, and automatic abstracting of scientific text. This algorithm can be used to solve the problem of automatic abstracting. To do this, select a fragment of text with the greatest semantic weight, as explained above. The result of development program is verified on the example of an ontology formed based on the exponential dictionary of computer science. Implementation of this algorithm should take into account cases where ontology graph contain critical nodes, which are the intersection of different paths from one concept terms to another, as explained on figure 11. Consider the case where there is a crossroads of paths leading from one concept of ontology to another. Assume the distance between nodes R and E along the path through node B is, as explained of figure 1. This example. Node E is the critical node with the crossroads of different paths, that path and this path. Calculate the distance between nodes from A to I in two ways. The first way take into account the critical nodes, and second way is to consider each path independently of the other. We obtain the different values. Thus, the presence of critical nodes does not allow use direct Formula 1 to calculate the distance between the concept of ontology in a way that ignores such critical nodes. Therefore, the algorithm for detecting nodes crossroads will be significant. A critical node is a node that corresponds to single minimum section of the graph. Namely, the smallest section is equal to 1. The problem of finding the smallest section of the graph is twofold of the problem of the largest flow. The well-known algorithm. This paper proposes a method of semantic analysis based on inverse-additive metrics, which takes into account the semantic distance between the terms of ontology in a text document being analyzed. This metric allows to correctly process a case where several paths in the oriented graph of the ontology from one concept node to another. Semantic analysis of scientific documents is considered as such texts have a clear structure. The concept of semantic distance between the terms of scientific text and semantic weight of scientific text is introduced. The semantic weight of individual fragment of scientific text can be used to solve the problem of automatic abstracting. Some of the difficulties in implementing the proposed approach related to critical nodes on the path in the oriented ontology graph from one concept node to another are discussed. Next, the list of reference used, and that's all. Thank you for your attention.
Thank you so much for your presentation. So, are there any questions to the speaker? Dear colleagues? Okay, if no, we will proceed. So do we have any participants who appeared, because we are a little bit faster than expected, because it seems to me everyone has spoken already. Maybe we will do in this way.